Okay, in this video we are going to talk about volumes by slicing using different methods. We're going to find volumes of various three-dimensional objects. First thing we're going to really think about is taking some three-dimensional object, whatever that shape might be, and we're going to actually cut it into smaller slices and finding the volumes of the smaller slices first and then adding them up. That's sort of the underlying idea behind this. Think of it like slicing a loaf of bread. And so what you're really going to think about is you're going to break it up into smaller sub-intervals, all of which have length, ending minus beginning divided by however many slices you want to have. And you're going to start to realize that what we're going to do is we're going to add up the volume of each of these small slices. And as we add up those volumes, that will give us a good estimate for the exact volume. But if you remember, if we take the limit of that sum and actually have infinitely many, then we're actually going to have an integral, which will in fact give us the exact volume. So that's sort of the big picture idea behind what we're going to do here. So the first method that we're looking at is called the general slicing method. So suppose you have a solid object that extends from x equals a to x equals b. And we're going to think about what that cross section looks like, or what that slice of the loaf of bread looks like, if we can find the area of the face of that, and then multiply it by a width. That would give us a volume. And that's exactly what the Riemann sums really are doing, just now in 3 dimensions. And so then this is that formula that we're going to be using to calculate that. So let's go through and just do this first example to make some sense out of this. So we're going to use the general slicing method to find the volume of a solid that has a semicircular base of radius 5, and then the cross sections, we'll be able to draw that on top, what those cross sections are going to look like. They're going to be perpendicular to the base and parallel to the diameter. So let's try to visualize what it is that we have going. I'm going to draw this first in just 2 dimensions, and then we can visualize the 3-dimensional piece after. So the base of my solid looks like a semicircle. So I'm going to draw that semicircle right here. This is the base. And then this has a radius 5, so we can label it. That's going to go up here to 5 and down to -5. Okay. And then we're going to think about the cross sections are going to be perpendicular to the base. That just means they're popping out of the screen at you, perpendicular, directly straight out at you, but parallel to the diameter. So this will be something like this, parallel to the diameter, and then that little sliver right there is going to pop out at you as a square. In this case, they're going to be squares. So we need to find the area of those squares. So in order to do that, I'm going to go ahead and find the equation of that semicircle. And it's easier if once we are going to go through and integrate, just if I can try to get one variable by itself, it looks like I have y equals plus or minus the square root of 25 minus x squared was the equation of that circle. And the reason I'm going to think about that is if you look at this square that I've got right here, we are actually going to think about the height of the y value here is going to be half of the length of that whole square. So the y value just goes from here to here, but we want the entire square, which is going to be twice as big. So let's actually write that down. And so we're going to think about that as the side length of the square is going to be twice the y value, which really means, and let's just call that S for side length, is going to be twice the y value. But if you realize we already got y by itself, so that's actually twice the square root of 25 minus x squared. All right, and then we want to think about the area of the square. So of each of those squares that are popping out at the page at you, we want to be able to find the area of those. And that area of every square is the side length squared. So our area is going to be twice the square root of 25 minus x squared, but all squared. Okay, so then if I were to simplify that, I'm going to get 4 times 25 minus x squared. I'm going to go ahead and just simplify one more time to make it easier for us to integrate later on. Okay, so what we have so far is we have the area of each of those squares that are going to be popping out at you. We have a formula for that, and then that means we know now what the volume is going to be, because we also have a formula for the volume using this method. Okay, so let's go ahead and do that. So now all we have to do is integrate that. So my volume is going to be the integral from 0 to 5, and let me go back and show you why it's from 0 to 5. 0 was the first x value, all the way up till 5 was the next x value, because this semicircle had radius 5. Okay, alright, so the integral from 0 to 5 of 100 minus 4x squared dx. That was our area. The integrating the area is going to give us the volume of this whole solid. Alright, so then we can just integrate that to be 100x. It looks like then minus 4x cubed over 3 evaluated from 0 to 5. And then we can plug stuff in. I'm going to get 100x minus 4/3 times 5 cubed is 125. And then minus, it looks like when I plugged in 0, that bottom bound, it looks like I just got 0 anyways. Oh, whoops, I forgot to plug in. Oops, sorry about that. We forgot to plug in the 5 right here. Okay, so that would be obviously times 5 when I plugged in 5. Okay, so then I'll have 500 minus 500 thirds, which is a total of 1,000 thirds units cubed. All right, and that's the volume. Ta-da! All right, let's go through and do a few more examples so we can visualize what's going on. We're going to jump straight through and do the next method, which is the disk method. So another method for finding a volume of a three-dimensional object. This one's a little bit different. What we're going to do is have some two-dimensional region that we've got shaded in here, and then we would revolve this about the x-axis. So once you revolve this around the x-axis, you can see that each little sliver is going to create a disk, which is where it's going to be like a circle, and the area of each of those circles is pi r squared, and that's why the volume will be the integral of that pi r squared. And our radius in this case is the height of that function. You can see that the height of that function, once you went through and revolved it all the way around the x-axis, the height of that function would be the radius of that circle that we're creating. Okay, so that's the idea of the disk method, and that's why we're using then this formula that we have here, which is still going to be an integral of the area, but that area now is in terms of disks or circles, which is where the pi r squared comes from. Okay, all right, so let's do that first example for that problem. So we're going to have some region bounded by the curve f of x equals x plus 1 squared. So let's go ahead and graph that first. X plus 1 squared is a parabola shifted over here to -1 is where that's shifted over at. And we care about this from x equals 0 to x equals 2. So it looks like this is the region in question that I am then going to revolve around the x-axis. All right, so then using the disk method, our volume is going to be the integral from 0 to 2. Those are our bounds that we have here from 0 to 2. And then it's going to be pi times our radius squared, or in this case, the height of our function squared, dx. And then we're going to simplify. I'm going to go ahead and take the pi on the outside of the integral. Makes it a little bit easier to integrate it because pi is a constant multiple. We can do that. X plus 1 squared squared becomes x plus 1 to the 4th. And then we can integrate that as x plus 1 to the 5th over 5 evaluated from 0 to 2. So it'll have pi times, it looks like 3, well, let me actually simplify that, 3 to the power of 5, sorry about that. Okay. 3 to the power of 5 over 5 minus pi times 1 to the power of 5 over 5. And that is going to be our volume, there we go, units cubed. That's going to be the volume of that region after we've revolved it around the x-axis. Okay, excellent. All right, let's go ahead and do another one. So the third example, third method to be able to visualize what it is that we're dealing with for these volumes is going to be the washer method, which is really the exact same thing as the disk method that we just did, although instead of it creating, when we do a revolution, instead of it being a full circle, it might actually have maybe a hole in the middle, so it looks a little bit more like a washer. That's why it's called the washer method. So let's draw this first couple of graphs so that we can visualize it. The best thing to do is to always make a sketch first. If you can graph it first, it's always going to be more visual. So it looks like here I've got R is a region bounded by y equals 2 root x and y equals x in the first quadrant, so I'll graph each one of those. So here is my y equals 2 root x, and then it looks like I have y equals x, and I'm only drawing it in the first quadrant because that was all that this problem was asking me for. So that's the region in question that we are going to pick up and revolve around the x-axis here. So we do, it looks like you can see that we have the 2 root x is on the this graph, this red one, is going to be on the outside of that region the entire time. And then it looks like that blue one is going to be on the inside of the region this entire time. So when you're thinking about this formula that we have, you're really thinking of it as pi times the bigger radius squared minus the smaller radius squared, because we are actually subtracting that smaller radius, or that hole in the graph. All right, so in order to do this, we need to find the intersection points first. So let's go ahead and find those intersection points first. Okay, so in order to do that, I'm going to set those two equals to each other. I have x equals 2 root x. You can square both sides, or you can maybe just do a little bit of yoga for the brain. Think about it, and we're going to end up with x equaling to 4 is that intersection point that we have. So then our volume is going to be the integral from 0 to 4, pi times the bigger radius squared minus the smaller radius squared. Okay, and then we can simplify it from there. I'm going to bring the pi on the outside again. It's a little bit easier to integrate that way. That's all there is to that. And then I'll have, it looks like 4x minus x squared dx, which is a total of pi times 4x squared over 2 minus x cubed over 3, evaluated from 0 to 4. So I will have pi times, it looks like I will have 32 minus 64 thirds minus 0 when I plugged in 0. So we will get a total of pi times 32 thirds once we combine those like terms. Again, units cubed because we found a volume here. All right, so those are our 3 different methods. Ta-da!